So we're going to learn about friction today, and friction is actually relatively simple. It's got only two cases, static and kinetic. So static is when something is standing still, and kinetic is when something is moving. So I'm going to draw this refrigerator, and I'm trying to move a refrigerator. I don't know why, because I'm not strong enough to. And this is important because this is where static friction comes in. That you can be trying to move something and it's not going to move. And why is that? Well, there's a force that I am pushing on this refrigerator. Let's say this is, 10 newtons. Well, there has to be a force if the refrigerator is not moving that is pushing back with also 10 newtons, right? And also because of Newton's third law, with every action there's an equal and opposite reaction. So there is a force, not on me, I should say on the refrigerator here, that is going back with the same force that I'm pushing it because it's not moving yet. So coefficient of static friction works like this. So friction, whether it's static or kinetic, the force due to friction is the coefficient of friction, which we call mu. It's like the same Greek letter we use for micro in units, times the normal force. So the coefficient of friction does not have units. So what do I mean when I say the normal force? Well, the refrigerator, let's say it's 100 kilograms, is being pulled down with some force of gravity. Well, because it's not sinking into the ground, it must be pulled or pushed up with the same force, which is the normal force. So pretend those vectors are the same length, because they're supposed to be. Well, if gravity is the mass times the acceleration due to gravity, which is a constant, then I'm going to call gravity negative because it's going downward, then this is positive, the same thing. So this actually turns out to be 1,000 newtons, so let's rewrite this as 1,000 newtons and negative 1,000 newtons. So we said I was pushing this fridge with a force of 10 newtons, right? So this is how we can figure out the coefficient of static friction, and I'm calling it µs for static friction because I know my fridge is not supposed to be moving. So I can say that the force due to friction, which must be 10 newtons, going backwards here. So this is 10 newtons, equals the static friction coefficient times the normal force, which is 1,000 newtons. So that puts our static friction force at 0.1. And it's often going to be a decimal like this. So here's how static friction works, is it always has to equal the force with which the thing is being pushed or pulled, because the thing is not moving. So static friction, the coefficient, that goes here, the coefficient is going to be equal to some product of the force until it gets to a certain point, and then it's going to max out. And when it maxes out, if you put a force that's more than its maximum value, then your thing is going to move. So the kind of information that you'll get for a static friction problem is similar to the kind of information I gave you. You have to get out of the friction, the static friction coefficient, and the normal force, you have to get 2 of them out of 3. Or you have to have some way of getting 2 of them out of 3. Now let's say that we're talking about kinetic friction. Now something is moving, so let's go back to something that we observed in one of the earlier videos where we had an ice skater who is skating forward with some force. And we'll call this, 5 newtons, right? And let's say that this person is going at a constant velocity of 6 meters per second. Now, the number 6 meters per second isn't going to end up mattering. The point is that the velocity is constant. Because if something is going constant velocity, it has to be going, or has to not have any net force on it. So, therefore, the force due to friction must also be 5 newtons, right? By logic. So This person is also being pulled down by gravity, with some gravitational force equals the mass times gravity, and is being pulled up or pushed up with a normal force that must be equal to the negative of the mass times gravitational acceleration. All right, so let's say that this person is, 60 kilograms. Why do they have one arm? There we go, 60 kilograms. And I want to figure out the coefficient of kinetic friction. So how are we going to do this? Well, the formula is essentially the same. The force due to friction equals the kinetic friction constant, which this time it is really constant. It's not weird like the static friction coefficient where it changes. You have a material, it's got a kinetic friction constant, and that's all there is to it, and it's going to be multiplied by the normal force. Well, the normal force, the magnitude of the normal force is the mass times the acceleration due to gravity. So in this case, 60 kilograms times 10 meters per second squared. So this is going to be the gravitational force is going to end up being negative 600 newtons. So then the normal force must be positive 600 newtons. That's going to be plugged into our equation here. So we have 600 and we have our force of friction is 5, which didn't make a lot of sense, I'll admit. But if we end up doing this equation, then this must be 5/600ths, which probably goes into some nice decimal that I don't know. So that's how to find the kinetic friction constant. So these examples seem pretty simple. We can do some more complicated things with this. So for example, a common thing in physics that I hate with a burning passion is called an inclined plane. And it looks a little like this. Looks like a hunk of cheese. And you're going to get some angle that it's on. And let's say that I have a block that's sitting on this inclined plane and it's 2 kilograms. And it is moving down the incline with a constant velocity of 3 meters per second. Now here's my question to you is, does the 3 matter? Well, once I tell you what we're solving for, it doesn't. We're solving for the constant of kinetic friction. So we don't actually need the velocity. It's just telling us that the net forces add up to 0 because it's constant. So from here, all we have to do to get the constant of kinetic friction is a bunch of math. So I'm going to say mu k equals question mark. This is what we're trying to find. So now we're going to figure out what forces are acting on this block because that's going to help us to figure out the friction, right? So you know how normally we have everything in vertical and horizontal components? Well, in inclined planes, it's actually kind of messed up because we're doing everything in the components of what is parallel to the inclined plane and what is perpendicular to the inclined plane. So, for example, gravity is going this way, right? This is the force due to gravity, which is equal to the mass times the acceleration due to gravity. But we need to split it up into components that are parallel to and perpendicular to the inclined plane. So we're going to have a parallel component going this way. So this is how the block is sliding down. We're going to have a perpendicular component that's going this way. And this is pushing straight into the incline. So this is going to end up being some form of sine or cosine because if that's 30, then this is 60 because of complementary angles. So, like this is 60 and this is 60. Those two are actually, no, it's similar. They're similar. So we have our hypotenuse is going to be the mg thing. And then what we're looking for, which is going to be this component here, is an opposite. So we're going to do sine of 60 equals what we're looking for divided by the force due to gravity. So what we're looking for is going to be equal to mg sine of 60. So the other one, it's the same thing except it's cosine. So this is just doing ca instead of so, and we're going to get that. And so the reason that we split it up like that is the one that's going straight into the inclined plane, well, our object, our block, is not going into or out of the plane. So there's got to be a force that's exactly counteracting that. But we're assuming that our object is sliding down the plane because it's got a velocity of 3 meters per second. So that other one is going to be counteracted differently. So here's our normal force. It's going straight out of the inclined plane. And that's going to be equal to the other component that we found that's going straight into the inclined plane. So it's going to be mg sine of 60 degrees. So the other one is going straight parallel with the inclined plane. So what is counteracting it? Because our object is not accelerating, so again, it's got to have a force that's equal. So this is actually our friction force, and it's going to be equal to mg cosine of 60. So again, the reason that we know all these forces are counteracting each other is because we do not have an acceleration. We have a constant velocity, which means our net force is 0. So we got our frictional force by taking a component. But then why do we take the other component? Why do we bother to get the gravitational force going into the incline and the normal force going out of the incline? Well, because we need the normal force, right? So if we're going to do this solving for the constant of kinetic friction, our frictional force is equal to the constant times the normal force. Now we have the frictional force and we don't have the constant, so we need the normal force. And we have the normal force is here. It's the one that the inclined plane is pushing up the object with. So we've got mg cosine of 60 equals our kinetic friction constant times the other thing, the normal force, which is mg sine 60. And this actually works out pretty nicely because we can cancel mg, or the mass, times the acceleration due to gravity out of both sides. And then we get cosine 60 equals mu k times sine 60. And so our kinetic friction force, or not force, constant, is going to be equal to cosine 60 divided by sine 60, which, if I remember right, is the same thing as the cotangent of 60. And you can just plug that into your calculator. So that's how to deal with the awful beasts that are inclined planes.